Okay, I got the authorization to start. So welcome to the third session today. The first speaker is Daan, who is going to talk about compiler support for control flow linearization using architectural Mimicry. Please go ahead.
Good afternoon. My name is Daan and I'm a PhD student at Distrinet at KU Leuven. And I would like to present a compiler-based defense against side channel attacks that makes use of a novel hardware defense called architectural mimicry. Before talking about our compiler defense, I'll give a short introduction on microarchitectural attacks. And then I'll explain how to linearize control flow, after which I'll talk about how we implemented this in LLVM. Finally, I'll discuss some experimental results. A microarchitectural attack is an attack where an attacker tries to get information about some secret data based on microarchitectural state that's shared between the attacker and his victim. For example, an attacker might be able to figure out if a branch was taken or not based on timing differences or other updates to microarchitectural state, which could leak a branch condition. Another example is the leakage of memory addresses through cache state. But with our defense, we focus on eliminating leakage through control flow. So the example on the left. And one way to defend against such attack is to make the side channel leakage independent of secret information. We assume the common constant time leakage model, where memory addresses are leaked by load and store operations, and secret dependent branches leak their branch condition if the execution time or other microarchitectural state is different depending on whether the branch was taken. And under this leakage model, we need to eliminate all secret-dependent branches by linearizing them. And the state-of-the-art method to linearize is to execute both branches and then use some kind of constant time selection primitive to discard the results of one of the branches. But this comes with some overhead, especially on architectures like PriSC'24, where there are no dedicated instructions that could be used for constant time selection. This is where architectural mimicry comes in. Architectural mimicry, or AMI, is a new hardware extension developed by my colleagues at Distrinet, which provides new ways to balance and linearize code. They implemented this as an ISA extension to RISC-V. And it introduces a new execution mode called mimic execution, in which instructions have the same microarchitectural effects, but some architectural effects are suppressed. For example, a load instruction in mimic mode will load from the given address and touch the same cache lines, but it won't actually store the result in the register. Different instruction qualifiers can be used to control the mode of execution. By default, instructions have the standard qualifier, which means that they are executed normally in standard execution mode and mimicked in mimic mode, but the behavior changes if the instruction has different qualifiers. For example, a persistent instruction is always executed in both modes. And this is a basic example of how we can apply AMI to linearize a secret-dependent branch. We replace the branch with an activating branch. This means that instead of jumping to the target location, block 3, we will instead enable mimic mode until that block is reached. And then always continue the execution at location 1, regardless of the value of the branch condition. So in this example, we'll always jump to block 1, and in the case that instructions at location 1 and 2 are mimicked, the value in V won't be affected because mimic mode is enabled. So that way you get the same behavior as the original program on the left without actually jumping to a different branch. You always observe the same microarchitectural effects. Unfortunately, the authors of AMI don't have full compiler support. They only provide an assembler. So all transformations to the code have to be done manually, which is quite tedious. Furthermore, their programming models assume structured control flow graphs, like the one on the previous slide, but it doesn't. Their programming models, they don't generalize well to other kinds of control flow that you would commonly encounter during compilation. With these limitations in mind, our goal is to automate control flow linearization of reducible control flow graphs. Here are some examples. On the left is a structured control flow graph, which consists out of these nested if-else constructs. And that's the only kind of control flow graphs that their original programming model supported. But compiler optimizations often transform control flow graphs, such that it's no longer structured, and the term reducible is used to describe control flow graphs for which loops can easily be analyzed, and here is an example of this on the right. Which brings me to our main contributions. We've generalized the programming models to support reducible control flow, and then we extended the LLVM compiler with support for control flow linearization. And then finally, we also evaluated our implementation on a few micro benchmarks and compared different approaches. The method we implemented is based on partial control flow linearization by Moll and Heck, which was introduced in the context of SIMD, but it can also be applied to mitigate against side channel leakage. And this method can be used to linearize any reducible control flow graphs, and we can adopt this method a bit to make use of AMI. So let me show you how this works with an example. In this reducible control flow graph, we assume that block 0 has a secret dependent branch and that we need to linearize. And we also assume that we have a compact topological order of the blocks, shown by the numbers on the blocks. We start by visiting block 0, and we first linearize this branch by removing a control flow edge to block 4 and replacing it with an activation of mimic mode. This means that we'll unconditionally jump to block 1, and depending on the branch condition C, we'll enable mimic mode. And mimic mode will remain active until block 4 is reached. But to make sure that block 4 will always be reached eventually to disable mimic mode, we need to make sure that all paths that start in block 1 eventually pass through block 4. So that's why we add a deferral edge from block 1 to block 4. And that's a kind of a temporary edge that we used to remember that block 4 must post-dominate block 1. Then we visit block 1, which we don't need to linearize because it doesn't contain a secret-dependent branch. So we simply shift the deferral edges to its successors to maintain this post-dominance relation. When visiting block 2, things get a bit more tricky, since in this case, the deferral target is block 4, and block 4 comes before the successor, block 5. So in this case, we have to make sure that control flow goes to block 4 first, otherwise we're too late and we'd still have to go back to block 4 after going to block 5. So the deferral edge now becomes a new control flow edge, but we don't want to change the behavior of the program by introducing new control flow edges where there weren't any before. So to do this, we can make sure that this newly added edge is only taken in mimic mode. So that's why we can enable mimic mode in block 2. This means that if we're executing block 2 normally, mimic mode is always enabled before moving on to block 4. But if we are mimicking block 2, deactivating jump in block 2 does nothing, and we end up disabling mimic mode in block 4 because block 4 is the target of deactivating branch in block 0 that enabled mimic mode. The intuition behind this is that when we're in standard execution mode, we need to take the correct path according to the original control flow graph. But when we're in mimic mode, it doesn't matter what path we take, as long as our path leads to the target of the activating branch that enabled mimic mode. So that way we can freely add any control flow edges without affecting the correctness of the program. Finally, we add a new deferral edge from block 4 to block 5 because we created the new activating branch. The next block we visit is block 3. Here the deferral target and the successor are the same, so we can simply remove the redundant deferral edge. The next block we visit, and then we can do the same for block 4, and we don't need to do anything for block 5. So now we visited all the blocks and we've completed the linearization of the secret-dependent branches, which is only the branch in block 0 in this case. But in order for this transformation to be secure and correct, a few additional conditions need to be satisfied. To be secure, standard execution mode should be indistinguishable from mimic mode. This means that inside the secret-dependent branch, we need to leak the same information in both modes. For example, we need to make sure that loads access the same memory locations, even if the results are discarded. And we can do this by using persistent instructions to compute the address that's being loaded from. These instructions are executed in both standard execution mode and mimic mode. However, an activating region is only correct if the live state is unaffected in mimic mode. This means that persistent instructions should not write to registers that are live and entering the activating regions. And this is why in the implementation we had to constrain the register allocator to make sure that those persistent instructions use free registers. Now I'll give an overview of how we've implemented this in LLVM. The first thing we implemented is the ability to mark secrets in C code with annotations using this annotate type attribute. The analysis and hardening passes need to be implemented in the backend of LLVM, so we need to propagate those annotations to the backend. First, we lower them into function argument attributes in the intermediate representation of LLVM. And then we need to lower them to machine IR, which is the intermediate representation of the backend. But to do this, we had to go through the selection DAG first, before we can emit machine IR pseudo instructions. Now I'll give an overview of the hardening passes that we've implemented. So first there's a set of analysis passes that run. The first analysis pass is a taint analysis pass that finds the secret dependent branches based on those annotations. Next is a linearization analysis pass that determines a set of activating edges and new edges, but doesn't apply any changes. And the last analysis pass is a pass that determines which instructions need to become persistent instructions to ensure that branch conditions and memory locations are computed persistently. Based on this information, we prepare for register allocation by adding some constraints, which we do by inserting temporary instructions. Then register allocation takes place, in which a physical register is assigned to each virtual register. And then we run the same three analysis passes I described before again. The main reason we did it this way is that it was a bit easier than trying to maintain the results of the previous time we ran those passes throughout the register allocation. But this isn't an ideal solution. And finally, we applied the linearization by replacing the branches with activating branches and adding instruction qualifiers to the instructions that need to be computed persistently. Now I'll discuss the evaluation methodology and show some results. For the evaluation, we answered 5 research questions. Are the linearized programs still correct and secure? What are the performance results in terms of code size and execution time overhead? How do our different linearization methods compare to each other and to the manual linearization with AMI? And how does it compare to the related work? The general approach is that we run programs on Proteus, an extendable RISC-V core, and compare the execution traces that come out of it. We've only been able to evaluate our implementation on a small set of micro benchmarks, for which we have checked that the linearized code is indeed secure and correct. We find a code size overhead of around 6% when compared to the original insecure program. This is significantly lower than the methods that make use of conditional execution, where we find an overhead of around 55%. However, the manual linearization with AMI does slightly better and can achieve linearization with no overhead in most cases. Similarly, we find a 26% execution time overhead, which may seem high, but most of it is just a consequence of the linearization itself and can be avoided if we have to linearize. So since we need to execute all branch paths to ensure that we don't leak anything. For future work, it may be interesting to implement a security type system in the front end in order to detect violations earlier, which should result in a much better programming experience. Furthermore, being able to express AMI semantics in the compiler backend would be useful to avoid needing these register allocation hacks that we've been using. But it could also increase the correctness and security guarantees, which are at the moment quite low. So since we can't really run this on larger programs yet, and one interesting area of research is contract-aware secure compilation, in which a hardware-software security contract would be used to communicate microarchitectural properties to the compiler. And lastly, formal verification of these methods could be interested, or implementing this method in a secure compiler. We have some time for questions left, I think.
So, questions? Cool. Okay.
Hi, I was wondering whether there is any formal work describing the semantics. Do I understand correctly? There is no formal semantics for AMI?
I think there are some for AMI itself, but not really for the compiler linearization methods.
Okay.
Kathleen, then Gregory.
I guess it's a very naive question, since I was also not fully able to follow the numbers. So is the goal of AMI to make this kind of, or should I say, turning secret dependent branches into running to branches? Is the goal to make this faster? Or is it just a replacement for a simple instruction that selects the result at the end? Because that seems...
The goal is that it would be faster indeed, and that it would also be relatively cheap to implement in hardware, and it could still be faster.
So then two questions. Why would it be faster? And can you explain at which column we were supposed to look? Like which one was AMI on the previous slide? Yeah. I didn't understand how to read this graph.
So yeah, it's the linearization method that I've described is the one right here, and so that's around 1.26 on average, and the manual AMI linearization is 1.19 on average.
So this means using the hardware but doing the linearization by hand?
Sorry?
Using the hardware,
yeah, doing the linearization, which is slightly more efficient than doing it automatically with the compiler.
Do you have any, like, which one is the baseline in which you would really run one branch, then the other, and then select the results?
Like, that would be the 1.73.
I see. So that's the real improvement, right?
Yeah.
Even if you do it in the compiler, it's still much faster.
Yeah, so I'm wondering, so these secret annotations on variables, that seems like something that might be useful for other applications as well. Have you looked into whether something like that already exists, or whether there are proposals for that, or other papers that have something similar?
I think there is similar work, but I think it's usually more focused on the middle end and the front end, but not on getting this information down in the back end where we need it for a transformation.
Because I remember papers about other security relevant annotations that people have been proposing to add to C and to make use of in the compiler, like writes that seem not to do anything but are actually there for clearing secrets and so on. And so this seems like another case where you add security relevant annotations to C, which seems like something that would be nice to have in the longer run.
One last question. Couple of more. Yeah, we have time actually. Just a side.
Excuse me. So, does your optimization run after things like common computations have been lifted out of the branches that you're interested in doing? Like if you computed something in the top of both branches kind of by accident or something like that, or due to inlining, would that have already been lifted out, or?
I think that would have been done before.
Okay.
Last one. Yep.
Thank you for the talk. I have a quick question. Is there any uncompatible programs with your linearization approach?
Yes, we haven't really been able to test larger real-world programs yet because the compiler parsers aren't very reliable and polished yet.
I see. Thank you.
Speaker. Let's thanks again then.